Hi, my name is Abdulmalik Humayed. My presentation is about securing CAN-based cyber physical systems against denial and spoofing attacks. Our proposal is called CANSentry. Let's first introduce what CAN protocol is. It stands for Controller Area Network. It's very popular in many applications. It's even mandatory nowadays in cars for emission and testing purposes. It allows transmission in hostile environments, and because of its past topology, it reduces cost. In a typical CAN frame, we have this format and we care about the ID, arbitration ID. When we have multiple computers or ECUs, electronic controller units in a car, trying to transmit at the same time, they go through a phase called arbitration phase. We see here five ECUs trying to send at the same time, and eventually there is only one winner who has the lowest ID in terms of value. The lower the ID, the higher priority. There are a lot of attacks, and we care about two types of them: denial and spoofing attacks. For bus denial, they could be as simple as sending zero IDs. Sometimes an attacker can inject dominant bits, which are zeros, by exploiting some features in CAN controller called test mode, or even build a custom ECU. Sometimes an attacker would be interested in attacking a specific ECU instead of the bus. This could be realized by abusing CAN controller or even bypass it. And finally, by abusing error handling mechanism in CAN. Uh, final, Finally, we have the arbitration attack where an attacker could simply inject high IDs with high priority, or even inject single dominant bits in a selective manner, uh, and then fake partial frames to achieve certain goals. The other type or class of attacks is spoofing, where an attacker sends an ID that doesn't belong to its ECU. It belongs to where an attacker sends any CAN ID of her choice to spoof other ECUs. Um, ECUs could be compromised through a remote channel, and CAN frames are sent to unlock doors, stall the engine, or control the steering. For existing controls, um, there are different controls in the literature. Um, some could be classified as node identification and IDS systems. Others rely on um, scrambling, if you will, the CAN IDs in a way that an attacker would be confused. Also, another way is to counterattack the attacker. And authentication is a popular um mechanism and firewalls. We noticed that most of these solutions require major software and hardware modifications. They require changes in the protocol that may require all ECUs to be updated. They could introduce overheads because of the key management requirements. They also cannot defend against abused or compromised CAN controllers. They assume that there are complete frames to be dealing with. They don't consider the recent attacks where an attacker has the capability to inject single bits or incomplete frames. There are 10 categories of denial and spoofing attacks, and the existing mechanisms could detect or prevent some of them. But none of these mechanisms provide low-cost, real-time defense against all attacks. So an attacker could gain access to the bus through physical or remote access. There are two types of attackers depending on their capabilities. The first one we call the CAN abuser, where the attacker has complete control over a specific ECU software, but not the hardware. This attacker can abuse arbitration and error handling mechanisms to achieve malicious goals. The other attacker, which we consider a stronger model, where the attacker skips CAN controller, so to get a direct access to the bus. This could be realized by using a custom microcontroller that is directly connected to the bus, or by manipulating the CAN controller's I/O pins to directly access the bus. The attacker doesn't comply with CAN standards. What we mean by that is the attacker doesn't wait for the arbitration phase to start sending, the attacker is able to interrupt. The attacker can also send error frames without any errors present in the bus. For the denial attacks, the goal of the attacker in these cases is to enable certain functionalities in a target ECU or the bus. So for the ECU, when it's targeted by a denial attack, the ECU is shut down. The bus gets occupied. When we talk about arbitration denial, a specific CAN ID cannot win arbitration because it's under a denial attack. The spoofing attacks, when an ID is transmitted that belongs to another ECU, so the receiving ECUs on the other end are spoofed, which might result in disabling brakes, taking control of the steering wheel, or even false data injection, like the speed, the fuel level, and so on. We propose a stealthy attack that is selective, stealthy, and practical. The attack simply, we passively monitor the bus to detect a targeted ID during the arbitration phase. We overwrite the last recessive bit in that target ID, so we win arbitration. We wait until the very last minute to win arbitration. Then, to avoid triggering the error mechanism in the bus, we complete the transmission by injecting a fake frame. We faced a few challenges to implement this attack. Existing tools only deal with complete frames. A high degree of precision is needed. Unexpected delays, premature injection, or malformed frames may cause incomplete frames, resulting in bus errors. That's why we have to do it with high precision. Here we see our platform. We have this instrument panel from a modern car, simulate some ECUs, and this is the attacker device, and we here simulate the bus. As we mentioned, this type of attacker is called the skipper, where the attacker skips CAN controller and directly connects to the bus through the CAN transceiver. We evaluated our attack, and we find it to outperform other ECU and arbitration denial attacks. And the way we considered it stealthy, because it didn't cause any errors. These are the error counts. and it's selective because it only affects the targeted ECU or ID. It doesn't have any collateral damage, if you will. Now let's talk about the solution for our attack and other attacks as well. We proposed this novel firewall that basically sits between any ECU that we consider high risk ECU and the rest of the bus. What we mean by high risk ECU is any ECU that has a remote access or that has an open hardware access like the OBD port. CANSentry basically monitors the incoming traffic from this high risk ECU. It ensures that the consistency between the CAN bus state and the ECU state is maintained at all times. For example, when an ECU in the bus wins arbitration and starts transmitting, this high-risk ECU shouldn't interrupt the traffic. This is a basic concept that could be violated by malicious attackers. We use some rules to block illegal traffic coming from this high-risk ECU. We implemented this firewall with a low-cost and high-efficient platform. This is the architecture of our firewall. We see here that this is the bus. We call it CAN internal bus that we assume is safe. So we have this ECU, and we can have more than that connected to the bus. And this is the high risk ECU where it connects to the bus through CANSentry. We see CANSentry has two interfaces, one dealing with the high risk ECU and another one with the internal bus. So we mentioned that the main goal is to maintain a consistent state between the internal main bus and the external bus facing the high-risk ECU. We have two types of states, the CAN node or ECU states, and also another type which is the CAN bus state itself. The transition of these states is that we mainly trying to make sure that at any time the high risk nodes on the external bus, they have to operate in a state that is consistent with the state of the internal bus. This is the main goal. For example, if the state of the internal bus is idle, there is nothing happening there, nobody is sending, the consistent state in the external bus could be either idle or receive, it could be arbitration, or could be transmit. Any state of these is considered consistent with the state of the internal bus, and so on. Let's take this example. We have three rules basically, and I'll talk about rule 1. So when the internal bus is either in transmit or error flag state, the firewall always forwards the traffic from the internal to the external bus, and it blocks the traffic coming from the external to the internal bus, regardless of the state in the external bus. We give more priority to the internal bus because it contains secure environment, we assume, more secure than the high risk ECU. CANSentry has a filtering mechanism to prevent spoofing attacks. Another feature in CANSentry is filtering CAN IDs. So the way it works is that when the external bus happens to be in arbitration state, the firewall forwards traffic that has a CAN ID which is in the arbitration whitelist and confirms to CAN specification from external to the internal CAN bus. The reason we do that is that we prevent spoofing attacks. Spoofing attacks are very common and very hard to prevent. They could be detected, but to prevent them in real time, this is a really big challenge. We managed to do that using automata, so we can have efficient CAN ID matching. We see in this example at the bottom we have 4 CAN IDs, and we check them 1 bit at a time to make sure only allowed IDs go through to the internal bus, otherwise they will be blocked. This is the implementation of our design. We see here this is the attacker, this is the firewall CANSentry, and we see that it sits between the internal bus and the external bus. So the attacker goes through the firewall before she can send anything to the internal bus. And for more realistic traffic, we also added this instrument panel from a modern car. The evaluation that this firewall works, we tried 3 types of attacks: bus off and arbitration, and the stealthy arbitration denial attacks. And we see that in the top, this is the internal bus that we try to protect, and at the bottom we see the attacker trying to send some malicious traffic, but it has no impact whatsoever on the internal bus, and the same goes for the other attacks. CANSentry is deployed in physically secure environment, which makes it difficult to tamper with, and also it's simple, that it doesn't have a lot of interfaces, only 2 interfaces, external and internal. This makes it simple to manage and also difficult to compromise. And finally, because of its simplicity, the probability of having software faults is very small. We see here that our CANSentry, when compared with other controls, it outperforms them. And finally, to conclude, we summarized existing denial and spoofing attacks on CAN. Then we proposed and implemented a novel, stealthy and selective attack. Then we designed a novel firewall called CANSentry to defend against denial and spoofing attacks that violate CAN standards or abuse error handling mechanisms. CANSentry is the first solution that detects and prevents a broad spectrum of denial and spoofing attacks against CAN, and also it doesn't introduce noticeable overhead or delay, plus it's very cost effective. Finally, we thank our sponsors, and thank you very much for attending our presentation.